So when we're looking at these computer programs, we looked at function calls. One of the other things that will be important in the functions is local variables. So the point of this is going to be when you're looking at some of the code, understanding how you can see how variables are stored and then used to sort of understand what the original program flow looked like. So we're going to use the compiler explorer as well, so you can pull this up if you want to get a feel for how this works. So here's an example of a program that I brought up, right? And so I just made a little simple loop. I just added it into their power example here. And what you can see is that we have a standard loop, declares a local variable, int I in this case, and it sets the value of I to 0, runs through the loop, and then exits, right? So nothing too fancy. And what we can see is that if we look at, for example, setting this variable to 0, there's a location here where we set a variable to 0. And what does that look like? Well, we actually use a register R3, and we set that to 0 first, and then we store away the register to some memory location. So it's a two-step process. When we want to do the rest of the loop, so for example, we have a comparison here, you can see what it does is it loads the variable from memory, compares it to the end value, so it's while I is less than 5, so while I is 4, compares it to 4, and then either branches to here or continues the rest of the loop, which will increment, and then goes back. So there we can see our loop in assembly, right? And we can see a few spots where it's doing, right, this load here, adding, so this is our increment, and then storing it back. So we can basically see where it's running this, this load value here. At the same point, it's actually incrementing the num input as well, so we can also see a second part that's incrementing that. But if we just look at the loop variable, we can sort of get a feel for where it's located here. And what you can also see from this, right, is that the loop variable in the assembly version, right, there's no name, so there's no name that says this is I's, right? It's not telling you it's I, we have to infer that it's I based on how we're seeing it being used. So in particular, we see it being used with the comparison, right? We see that initial load to 0. So that's kind of how we can guess what it is. And this right here is actually an address in memory where it's being stored. And it's an address relative to FP. So FP is the frame stack pointer. So the stack frame, it's a pointer to that. And so it's just called the frame pointer, or FP. And it's going into some offset from that pointer location. And so we can see the other one, for example, is stored at -16, right? So these are actually different addresses. And we can see this -8 then coming up a few times, here, 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 here. So each time it's with the -8 offset, that's our I variable. So in general, where do they get stored? This was just one example of one compiler running one program, right? So it might just store it into registers. So if you look at this code, right, in theory, it could have used a different a register here, like R4, for example. And then it wouldn't have needed to actually store. So if we didn't have this here, right, it might not have needed to store this back, because R3 would always be, so if we did that, right, R3 would always be the last value that was incremented. So it wouldn't actually have needed to store it back to memory. So sometimes it gets stored to memory, sometimes it doesn't. It's going to be stored to memory, so not just in the registers, right? If the compiler runs out of registers, there's only so many. If the variable's declared static, it's always stored in memory because the value stays around. If it's a global variable, it's going to be in memory, it stays around. Sometimes it's just like an optimization thing that will change over time. So if you compile one program, it'll put it into memory like we have right here. Another time, it won't put it into memory. So there's no hard and fast rule, right, if it's just a standard sort of function. The important thing here is that the CPU can only perform operations itself on registers, right? So when I say register, that's like R3, R4, whatever that we're seeing in the code there. So the operations like the add, the load, the comparison, right? Those are actually operating on registers, sometimes a memory address too. But the value is always going to be put into a register before, the compare or whatever, XOR, whatever the mathematical or logical operation that's being performed. So you'll always see variables go from a register, or you'll always see the variables in the register, they will get moved from a memory. If it's stored in memory, it'll get moved to a register, operated on, and then stored back. If it's only using a local variable in the register, you just won't see that store back to memory. So the point here is that, right, just because you see it operating on like this comparison here, operating on R3, doesn't mean that R3 is the only location that local variable is being stored, because we also see it being stored into memory. If we set them as static, it varies a little. So we had here this frame pointer, right? So it's storing at some offset address. What we can also have is like an absolute address that doesn't change over time. So here I've simply put the word static, which says this value is constant, is kept between calls if we didn't initialize it. We could also have global variables, which would be accessible anywhere. And what you can see is that our load operation, right, before these operations were at some offset from the frame pointer, now we just see some label, L5, L5, L5. So this label is actually a fixed location in memory that is always operating, is always representing that variable. And you can see here, in fact, it's defining, right, just generally that this label is some location memory. So that FP, so I mentioned briefly, right, this frame pointer, FP is basically a location for where the stack frame is right now in memory. So the stack and stack frame should have been covered in like your operating systems course and stuff like that. But really briefly, right, if you remember, this is the location in memory that's growing as you do different calls. The important thing about this, so the important thing I want to highlight, right, is that this location is not necessarily fixed, right? So that's why we have an offset relative to the current stack frame. And so the local variables get stored on the stack in this case. Otherwise, here, right, the local variable, because it was declared static, even though it's local, was stored at some fixed, unique location in memory. So the important things, CPU only functions on the registers. And when I say CPU, this is like, the ALU if you want to get specific. We normally call it, but this is like your compare, right, your increment, or your add, or your multiply, things like that, right? They actually operate on register values. So you need to load from like memory, from RAM, into a register, operate on it, and store back. So you may have to do a bit of looking around, right? And you also want to watch out. So the other thing that's going to be important to take a look at is if we're looking at this code here, right, we see R3 used throughout. And R3 actually represents different variables. So if you look over here, we have the num variable and we have the I variable, right? They're all using R3 because the compiler loaded R3 here, right? Did a comparison. It didn't need to, it didn't store it back because it didn't change it yet, right? And now it loads a different memory register into R3. So now R3 represents num, right? Up here it represents I, num, and then it stores it away, and here it's loading I, so then it starts representing I. So that's the other thing to watch out, right? Because it's only using registers, it's going to have to reuse what register, or what's stored in what register. The local variables are normally stored on our stack frame. So we had that frame pointer that was pointing to what our current stack frame is. This memory location could be reused. So from a security perspective, that could be interesting because there's memory that in one One call, is storing some security critical variable, and another call it has some user input. And if that memory either isn't cleared correctly, isn't initialized correctly, there might be some security flaw, or if there's a way that we can, what we call overwrite. So if the computer isn't correctly checking how long each variable is, maybe we can write to the stack pointer, right, to the stack frame, and actually write beyond where we should be able to write. So if you imagine, in this example, there's just two variables here, but we could have multiple variables, and some of them could be like an array. So you can imagine that they're just stored at certain locations in memory, and it might mean you're able to overwrite that memory. And finally, global or static variables, and anything that's sort of constant throughout the program's execution really is going to be stored at a specific location in memory. And that memory won't be reused. So because it's a global static variable, you'll see a reference to a specific address, not some offset like we had in these examples here. So yeah, that's just a quick overview of what you'll see when you look at local variable storage in the disassembly language compared to when you look at just the straight C code.